Good afternoon, everyone. 1.3 million people die on the road every year. 1.3 million fatalities yearly. And if we think about it, it's equivalent to 10 big airplane crashes every single day. And we cannot accept this. Nexar mission is to solve the problem of car collision at scale, and this is how we do it. Nexar builds the world's largest open vehicle-to-vehicle network by turning your smartphone into a connected AI dashcam. The Nexar dashcam senses the environment around the driver, and the vehicle-to-vehicle network allowed cars to communicate with each other and to sense beyond the line of sight. By leveraging deep learning with millions of miles collected by our users, our technology provides a safer driver experience with the goal of solving the problem of car collision at scale and long before autonomous driving became a mainstream. Today I'll be talking about the challenges for solving the problem of car collision at scale. The first challenge is the limited compute power we have at the edge. The second challenge is the limited exposure to corner cases. The third one is to leverage our V2V network for safer driver experience. So what are the challenges for building a deep network on the edge? First, you need to build an efficient deep network to provide a real-time warnings. And also your model should be small enough in order to allow a continuous updates of the models over the air. Second, on the mobile, you don't have the privilege to run different models for each task that you have. All your tasks should run simultaneously while sharing all the computational resources across all tasks. For example, in our network we called Munet, we detect simultaneously objects at various scales, starting for large objects like bus and car and truck, to a very small object that could be up to a few pixels as traffic lights. Also, for each task that we have in our detection, we also want to recognize their attributes. For example, for detection of vehicles, we would like to understand if this vehicle is relevant to my driving direction or not, and we want to understand the lane level localization of this vehicle. For traffic lights, it is not enough to detect the traffic light, but we want also to understand the relevancy of this traffic light to my driving direction. We also would like to track all these objects over time, and all this should be done in a single-shot inference without compromising the high accuracy level. Our network consists of two main components. The first component is a ConvNet, which actually extracts feature maps for the input image. The second component, which we call the single-shot road understanding, consists of three convnets of detection, classification, and relative lane position. With this architecture, we are able to localize the vehicle, classify their type, and also to infer their relative lane localization. For example, in this image, you can see the bounding box in orange. You can see the one in the red marking. You can see that this is my driving direction, and the other one in green is the different lanes. Our second task is traffic light recognition. And this is a very tricky task because it's not enough to detect the traffic light and its states. This is relatively more easier task. But the challenging task is to detect if this traffic light is relevant to your driving direction. And in order to do it, you should incorporate the context of the road scene and understand the traffic light relevancy. For example, in the image on the right, you can see the top right traffic lights that are relevant to the straight driving direction, while the one on the left relevant to the left turn. And in order to understand this, our network should incorporate the global context of the image and even the road marks and understand which one is relevant to which driving direction. And this is not an easy task to do. So how we can extend this vehicle recognition network for traffic light as well? In deep learning, we need to take into account the trade-off between localization and generalization of the network. So the deeper you go in the network, the more generalization you get. But this comes with a localization cost because the receptive field becomes smaller and smaller. Since traffic light requires more localization and less generalization for the detection of the traffic lights, We add two conv layers on top of intermediate layer in order to detect the traffic light, to localize the traffic light and to detect its states. However, for relevancy, we need to incorporate the context of the scene, and therefore we put it on top of the last layer in order to get more generalization. For training, we use alternate training to iteratively train each task at a time with its own datasets. Here you can see the result of our network running on mobile. This is actually my ride to work with this iPhone, running in real time with running time, inference time of 50 milliseconds. On the left side, you can see the traffic light detection that are relevant to my driving direction. In the bounding box, you can see the bounding box is red, indicates for vehicles that in my lane, and the green one in a different lane. And the top right, you can see also my lane level localization, whether if I am in the second lane, or the third lane, or the first lane. So I'm able also to do 3 tasks simultaneously and run them on iPhone 7 device in real time. But not all our users are running Nexar app in the foreground. Some of them are actually running our app in the background while they're running their favorite navigation app, Waze or Google Maps. So Nexar unique scalable solution allow us to turn any dashcam, even a very simple dashcam, into an AI connected dashcam. So here you can see an example of a camera that you can buy, a relatively cheap camera, and you can buy it and pair it to the phone and run the Nexar app in the background. Recently, we managed to deploy a very efficient network that is actually running as a background task on the mobile CPU. So the application is running in the background while you're using navigation app or any other application that you're interested in, and the deep learning is running in the background. And we are actually one of the first company to run vision-based deep network in the background. Here you can see the results of the background network that detects simultaneously traffic lights, obstacles like cones, and police cars, with a running time of 3 milliseconds and CPU usage of 0.5 and model size of 20K, which is extremely small. This allows us to enable AI features also to our background user and to continuously update their models over the air. The second challenge I would like to talk about is the limited exposure to corner cases. And in driver assist, it's all about corner cases. Corner cases are the many rare events that needed to be covered in your training data in order to reach from 95 accuracy level to 100 or 99.999. Here you can see some few examples for rare events captured by our users, which clearly show that the road is unpredictable and there are a lot of corner cases. And this is only a few examples out of a lot that we have in our data, 20 million. Another example for corner cases is when the visibility is poor due to weather or light condition, and when traffic lights are very confusing, even for human drivers. Even for human drivers, it's hard to tell on the image on the right which one is relevant to my driving direction. Should I drive or stop? And traffic light relevancy is actually a very tricky task, even if the weather conditions are good. In order to address this challenge, we created a continuous deep learning pipeline for collecting corner cases and improving our deep models. First, a deep learning detector runs on the smartphone to collect potential rare events, like outbreaks or accidents. These events are then processed using multiple deep networks that are running on the server side with human-in-the-loop feedback for ground truth creation and for training our deep network on the server side. Once we have an improved deep models on the server side, our next step is to apply domain adaptation approach and to deploy our model in each city in the world. So we are able to deploy over-the-air models for each given city. So we have a specific model for New York, specific model for Tel Aviv, for Nevada. For each city, We actually have a specific model, also depends on the weather condition, if it's rainy, if it's winter, if it's snowy. So we adapt and continuously adapt the models according to the random distribution that we get from the random stream that we get from this specific city in order to optimize. With this pipeline, we already collected more than 20 million corner cases of driving videos and more than 100 million annotated images from over 80 countries. While our examples are very sparse in data and usually hard to obtain, we use a simple self-supervised approach to capture them by simply looking on mobile detection that are isolated in time and are more likely to be R-negative. Here you can see some negative example that's collected by this simple method that we're running on the mobile. And here you can see on the left, you can see detection of something that looks like a cones, but is not a cones object. On the right, you can see something that looks like a police car, but it's not a police car, and it's a good R-negative in order to improve our model. With this technique, we can continuously upload only the relevant information, the relevant images, the R-negative, because we don't want to upload all the data. We only upload the most important data that will improve our models. In addition to our vision model, we are also using deep nets on sensory data to detect collision. Here you can see two videos along with their sensory data. Now, by just looking at the sensor data, it's very hard to understand the difference between the spikes that we get and to understand whether it was a collision or not. However, once we augment the sensory data with the visual information, it becomes clear that the left one is a collision, is a true collision, while the one on the right side is not a collision, it was just a false positive sensor spike. So using cross modalities clearly improve the results. In addition, we also augmenting the vision with active mapping for understanding the traffic light relevancy, which is a very challenging task. Specifically, we run our multitask network with traffic light recognition and lane level localization on 100, here you can see an example, once we run the network on 1 million intersection videos in New York, and here you can see the same intersection that was captured by 4 different drivers. Once we run it, this network, together with all this data, we are able to create a map of traffic lights and to understand how many traffic lights are in the intersection, what is the relation between these traffic lights, and also the most important thing is to map between traffic lights to lanes. And this intersection is very challenging if you're counting only on vision, because there are 2 traffic lights that are really close by. You can see the 2 in the center, and each one of them has a different meaning. So for human drivers that are approaching the intersection at the first time, it's a very challenging task. But once we augment it also with the active mapping, we're able to provide high accurate solution. Recently, we also open sourced part of our data set with pixel level segmentation of objects and lanes, and also drivable area as part of our collaboration with the Berkeley Deep Drive Consortium. The BDD 100K is the largest annotated data set for road scene understanding research. Now I would like to show you some examples about how we leverage this machine vision technology jointly with our V2V network for safer driver experience. The first example is the traffic light countdown feature that we recently released in New York that tells the driver how long he has before the light turns to green. Here on the right, you can see the actual driver experience, the actual alerts that the user gets now in New York City that tells them exactly how much time they have before the lights turn to green. And on the left side, you can see our live map with traffic light prediction. So for every traffic light in New York, when we have an high precision, we can able to predict the cycle of the traffic light and to provide to user in real time the time to green. Another example is the police ahead alerts, in which we are able to automatically detect police car on the road and alerts other drivers through the V2V network. Here on the right, you can see an example for police alert, and on the left, you can see a heat map of police detection that captured just last week. So you can see all the distribution and where are they located and where are the alerts where they appeared. And this is just 1 week in New York. In addition to user features, we're also collaborating with cities to make them safer. Here on the left, you can see our mobile detector that is able to detect construction site objects. And on the right, you can see a web-based user interface that taking all this detection and map them to provide a fresh insight to construction site and lane blockages in the city. And we are already working with few cities in the US in order to improve their safety and in order to improve their infrastructure and to avoid road blockages in the city. One last example is the Nexar, which allows users to see through the car. This work is still in progress and is not running in real time, but it demonstrates our ability in the future to provide our user a superpower to see through cars and to get intersection movement assist alert for safer driver experience. You can see that we detect the car, and also we can, using another car, we can actually project the image and the video in order to be able to see through the cars. In conclusion, this is a major part of our vision of solving the problem of car collision at scale, and more people download Nexar and our network grows, our system becomes smarter and smarter, and we can save lives. And this is the amazing Nexar team that's turning our vision into reality. Join us to make the road safer. Thank you very much.